Okay, to work with a rational function that has variables in the numerator and denominator, it's a whole lot more work. So when we go to graph it, we're going to have a list of things to do, and that's going to be in the next section. In this section, we're just going to talk about wholes and asymptotes, which is a part of the process, but not all of the process. So vertical asymptotes is one of our types of asymptote. A vertical asymptote is going to be where the function is undefined. The graph can never, ever, never, ever, never touch or cross a vertical asymptote. And we've seen it's kind of like, bless you, the line of symmetry, how it has to be in a format to be an equation. It has to be in the format x equals a number. When a graph gets near that vertical asymptote, it has two options. It's kind of like, on the Roadrunner, when Wile E. Coyote would get, Roadrunner would get to the edge of a cliff, and he could just, run right up the cliff. Well, that's what a rational function could do. It either runs up the side of the cliff, or it runs down the side of the cliff. So this function, when the function gets near a vertical asymptote, the graph heads to either positive infinity or negative infinity. So how do we find a vertical asymptote? Well, the first thing that we're going to do is start with the original function and factor the numerator and denominator. Then the next thing we're going to do is see if there are any common factors. So if we can cancel any common factors, those are going to create wholes. We're going to have to study that a bit more later. So anything you can anything you can cancel is going to be a whole, and those x values are domain restrictions. Then we are going to set the denominator equal to 0. These are going to be the vertical asymptotes. And remember that those have to be x equals a number. And they are also domain restrictions. Okay. If you have a vertical asymptote that is there twice, like x plus 1 squared in the denominator, that's going to have multiplicity just like our roots did with our polynomial functions. So let's look at how those graphs would look differently depending on if we have even or odd multiplicity of our asymptote. Odd multiplicity of the asymptote is going to be like y equals 1 over x. That vertical asymptote will be at x equals 0, and we've graphed that one, y equals 1 over x. Remember that looked like the swoopty graph, like it was going along that way up here and going along that way down here. So if we have odd multiplicity, then our function is going to be headed towards positive infinity on one side and negative infinity on the other side of the asymptote. So it could be down on the left, up on the right, or up on the left, down on the right. If we have even multiplicity, like y equals 1 over x squared, we've seen that graph as well. Remember that graph also had a vertical asymptote at y equals 0, but it went up on both sides of the asymptote like that. So as we approach our vertical asymptote from both sides, the function heads towards infinity or negative infinity. To figure out if the graph goes up to positive infinity or down to negative infinity, we are going to use limits again. So let's look at this example here. Y equals x plus 2 over x minus 3. So nothing's going to cancel in this one. So we're going to find our vertical asymptote by setting the denominator equal to 0. So I set x minus 3 equal to 0, and that's going to tell me that I have a vertical asymptote at x equals 3. Now I know that when my function gets close to x plus 3, it's either going to zoom up or zoom down towards positive infinity or towards negative infinity. And that happens on both sides. But we need to figure out which is which. So we're going to use limits. So what we're going to do on the left-hand side of 3 is we're going to say the limit as x approaches 3 with a little negative sign up there. That means we're going towards 3 from the left-hand side of our function x plus 2 over x minus 3 equals, and I'm going to show you how to calculate that. So we're going to pick a number that's just a little bit on the left-hand side of 3. So like maybe 2.99. So this right here means as x gets close to 3 on the left side. With positive numbers, it's not too tricky. If this is our line x equals 3, then a little bit on the left-hand side would be like 2.99. So I'm just going to plug in 2.99 for x on both sides for every time I see the x in there. So 2.99 minus 3. And I'm not really concerned about what value I'm going to get because I know it's going to be infinity. It's either going to be positive or negative. That's what I'm concerned about. So really, I'm just looking at the sign. In the numerator, if I do 2.99 plus 2, that is positive. Denominator, 2.99 minus 3, that's negative. So this is going to give me negative infinity. So that's telling me that on the left-hand side of 3, the function is headed towards negative infinity. And then I do the same thing on the right-hand side. So I'll look at the limit as x approaches 3 from the right of my function x plus 2 over x minus 3. So this guy means as x gets close to 3 on the right side. So again, I'm going to play that same numbers game. I'm going to pick a number a little bit to the right of 3, like 3.001 or 3.01. We'll just go 3.01 because then we have the same number of decimals. I add 2 because I'm replacing the x with that number, and then 3.01 subtract 3. And again, I'm not interested in the actual number. I just want to know positive or negative. So 3.01 plus 2, that's going to be positive. 3.01 minus 3, that will also be positive. So this side is headed towards positive infinity. So I can draw my graph headed towards positive infinity on the right side. We're going to get more practice with this later. So this is just your first look at that. Just a reminder, this sum and difference of cubes is going to come up quite a bit throughout this chapter. So I thought it would be in our best interest to just kind of review it so that it's more fresh in your mind than from, whenever it was that you studied it years ago. So that sum and difference of cubes, there's f cubed plus L cubed, and then f cubed minus L cubed. So the kind of first thing you have to do is realize that you have this pattern and figure out what thing cubed is in this first space. So it might be like x cubed plus 8. Well, then f would be x because it's x cubed, and L would be 2 because 2 cubed gives you 8. So the pattern is always going to be the same for the numbers. We first have a binomial that starts with f and ends with L for both patterns. Then we have a trinomial that starts with f squared and ends with L squared, and in the middle has f times L. Then we have spaces for 1, 2, 3 signs. So the place what we're going to fill in the signs with is soap. So what that stands for is same. So that means the same as the problem. So in f cubed plus L cubed, that's going to be positive because it's the same as the problem. The O is opposite. So that's opposite of the problem, minus. And then the AP is always plus. So that one's always plus. So same sign, opposite sign, always positive. F cubed minus L cubed, same sign, negative. Opposite sign, positive, always plus, positive. Okay. Let's practice finding vertical asymptotes and holes. So remember that our first step is that we're going to want to factor, and then whatever we cancel is going to be a hole, and whatever we can't cancel will be a vertical asymptote. Then we're going to look at the behavior on both sides of the asymptote to see if the function is going to be zooming up or zooming down. So first off, we factor. We got f of x equals, it's x over x squared minus 4. That guy is difference of squares. So we got x over x plus 2 times x minus 2. Then we are looking to see, are there any holes? There are not, because nothing cancels. Then we will look for vertical asymptotes. And to do that, we set the denominator equal to 0. So we've got x plus 2 equals 0, x minus 2 equals 0. So our vertical asymptotes are at x equals negative 2 and x equals 2. So we've got 2 of those asymptotes. We have x equals negative 2 and x equals 2. And I want to look at the behavior on the left and right side of both of those. So here's my x and y axes. I know I have these two asymptotes, x equals 2, x equals negative 2, but let's check on the left side and right side. Like I said, the positive numbers are the easiest, so maybe we'll start there. So we need the limit as x approaches 2 from the left of my function, which is x over x plus 2, x minus 2. So remember when we're looking at the limit from the left-hand side, we're going to pick a value that is just a little bit smaller or on the left-hand side of 2. So I'm going to be replacing all of my x's with a number that is a little bit less than 2, so maybe 1.99. And then I just want to look at the sign. So if I replace this x with 1.99, the numerator will be positive. If I replace this x, 1.99 plus 2, that is going to be positive. 1.99 minus 2, that is going to be negative. So when I multiply all three of those together, or I multiply those two and have a positive over it, that gives me a positive divided by a negative. So on the left-hand side of that asymptote, the function is headed towards negative infinity. Then I do the same thing on the right. So the limit as x approaches 2 from the right, and that's x over x plus 2 times x minus 2. I want to replace each of those numbers, each of those x's, with a number that is a little bit to the right of 2. So maybe 2.01. 2.01 in all of those spots. When I make that replacement, the numerator is going to be positive. In the denominator, I have 2.01 plus 2, that is positive, and 2.01 minus 2 is also positive. So that's a positive divided by positive, which means on the right-hand side of x equals 2, the function is headed towards positive infinity. We'll do the same thing over here for x equals negative 2. Let's look at the left-hand side. Might switch colors here. Limit as x approaches negative 2 from the left of x over x plus 2 times x minus 2. So a number that's a little bit to the left of negative 2 would be negative 2.01. So I'm going to replace all three of these x spots with negative 2.01. Which is going to give me a negative number in the numerator. Negative 2.1 plus 2 would be a negative number. Negative 2.01 minus 2 is also negative. So I get a negative divided by a positive, which will be negative infinity. So on the left-hand side of negative 2, my graph is headed towards negative infinity. And then we'll look at the right-hand side of negative 2. So the limit as x approaches negative 2 from the right of x over x minus 2, x plus 2. Now a number just to the right of negative 2 would be negative 1.99. So I'm going to replace all of my x values with negative 1.99. So in the numerator, that's going to be negative. In the denominator, negative 1.99 minus 2 is a negative number. Negative 1.99 plus 2 is a positive number. So I have a negative divided by a negative, which is a positive. So that will be headed towards infinity. So on the right-hand side of x equals negative 2, my function will be headed towards infinity. Now, as we move into the next section, we're going to learn how to figure out what's going on in between these asymptotes. But for now, we're just sticking with poles and vertical asymptotes. Our next example, what is that one? F of x equals x squared plus 1.